Let me ask you something stupid. Why does a flame point up? Light a match. Light a candle. Light a campfire. The flame goes up. Always. Tip the candle sideways, and the flame bends and curls and finds its way back to pointing up. Hold the match upside down, and the flame still climbs toward the ceiling like a little orange tongue trying to lick the sky. It is one of those things you have seen 10,000 times in your life and never thought about for half a second, because the answer feels obvious. Heat rises. Everybody knows that. Heat rises. Done. Next question. I want you to hold on to that answer for a few minutes. Hold it tight. Believe it, because it is wrong. Or, all right, fine, it is not exactly wrong, but it is hiding something. It is doing a kind of magician's misdirection on you, and once you see what it is hiding, I think you will never look at a candle the same way again. Here is the punchline I am going to spend the next half hour earning. If you take a candle, and you light it, and you put it somewhere where there is no gravity, the flame does not point up. It does not point sideways. It does not point. The flame becomes a little glowing ball, a pale blue sphere of fire, sitting in the middle of the air, going absolutely nowhere. It looks like a tiny dim moon. It barely makes any light. Sometimes you can hardly see it at all. That is a real thing. People have done this experiment. Astronauts have lit candles in spacecraft and watched a sphere of fire form, just hanging there in the cabin, while the astronaut floats next to it and writes down notes. And the question I want to chew on with you is, what on earth is going on? Because that simple shape, that glowing ball, is telling us something profound about what fire actually is. Something most people, including most people who have lit 1,000,000 matches, have never thought about. So let us go back to the stupid question. Why does a flame point up? Let us pretend we do not know. Let us be genuinely confused, the way a curious child is confused, and let us follow the confusion wherever it leads. Because I promise you, by the time we are done, that little flame in front of you is going to look like a much stranger creature than you ever suspected. All right. Step 1. What is a flame? Stop and try to answer that. Out loud even. What is a flame? You might say, well, it is fire. Okay, fine. What is fire? It is hot stuff. It is burning. It is what happens when something burns. Right. But what is the thing? What is the actual physical object? Watch a candle for a minute. There is the wax. There is the wick. There is, above the wick, this dancing teardrop of light. Reach toward it, and you feel heat. But the teardrop itself, what is it? Is it a thing? Is it stuff? Is it matter? Sort of, but not really. It is more like a process, wearing the costume of a thing. A flame is not an object the way a rock is an object. A flame is an event that has been going on long enough to look stable. It is a chemical reaction made visible. It is a region of space where stuff is happening, and the stuff happening produces light, and the region of space stays in roughly the same place, so we treat it as a thing. But it is not. It is a doing, not a being. Let me explain what is doing. The wax in the candle is mostly long carbon chains. Hydrogen and carbon hooked together in chains, sometimes 20 or 30 atoms long, in a kind of waxy molecule. The wick soaks up the melted wax, the way a paper towel soaks up water. The heat from the existing flame turns that liquid wax into a vapor, an invisible gas rising off the wick. That gas, the wax vapor, mixes with oxygen from the air. And when the temperature is high enough, the molecules of wax vapor and oxygen smash into each other hard enough to break apart and rearrange. Carbon hooks up with oxygen. Hydrogen hooks up with oxygen. You get carbon dioxide. You get water. And along the way, you get a tremendous amount of heat and a tremendous amount of light. So a flame is a place. It is a place where wax vapor meets air, where the temperature is just right for them to react, where new molecules are forming as fast as the old ones can come in. It is a chemical kitchen with no walls, hovering in midair, replenishing itself at exactly the speed it consumes itself. Now look at the flame again with that picture in your head. The bottom of the flame, right above the wick, is dark. There is almost a little hollow space there, a tiny void you can see if you look closely. That is wax vapor, freshly evaporated, not yet hot enough to react. Then surrounding that is a faint blue zone. That is where the chemistry really kicks off, where oxygen first meets the fuel and starts breaking it apart. Then around the outside you have the bright yellow-orange tear shape that you actually call the flame. That bright part is not the chemistry itself. That part is soot. Tiny black specks of unburned carbon, glowing because they are hot, just incandescent particles, like the filament in a light bulb, but suspended in midair, formed and consumed as the flame breathes. So when you look at a candle, you are looking at a layered thing. Cool fuel in the middle. Hot reaction in a thin shell around it. Glowing soot around that. And the whole assembly is shaped like a teardrop. Pointed up. Why pointed up? Heat rises. Right. We agreed on that. Hold on to it. We are about to start poking it. Why does heat rise? That is the question. Most people, if you push them, will say something like, well, hot air is lighter than cold air, so it goes up. Okay. That is in the right neighborhood. But what does that even mean? What does it mean for one thing to be lighter than another, and so it goes up? Air is air. Why does air care? Imagine a swimming pool. Picture it. A pool full of water, summer afternoon, kids splashing. Now imagine I take a beach ball, push it underwater, and let go. What happens? It shoots up, comes flying out of the water like a little rocket. We have all done that as kids. The beach ball goes up. Why? Because the beach ball is less dense than the water. There is less stuff packed into the same volume, so the water surrounding it is heavier, and gravity is pulling on everything. Gravity is pulling the water down, and the water down, and the water has to go somewhere. So the water around the ball squeezes inward, gets under the ball, and shoves the ball out of the way as it falls. That is what we call buoyancy. The ball does not really want to go up. The water wants to go down, and the only way down for the water is to push the ball out of its way. Same thing in air. Hot air is less dense than cold air. The molecules of hot gas are bouncing around faster, flinging each other apart, taking up more room. Same number of molecules, more space. So a packet of hot air is like a beach ball under cold air water. The cold air around it, pulled down by gravity, falls past the hot pocket, gets underneath it, shoves it up. The hot air goes up because the cold air is going down and there is nowhere else for the hot stuff to be pushed. That is buoyancy. And here is the part everybody glides past, the part that I want to grab you by the shoulders and shake about. Buoyancy is gravity. Buoyancy is gravity working on differences in density. Take gravity away, and there is no down. And if there is no down, there is no up. And if there is no up, hot air does not rise. There is no rising. The whole concept does not exist anymore. Think about that. Heat rises is not a property of heat. Heat rises is a property of being on Earth. If you took a closed jar of perfectly still air and you let it just sit, the cold air would not be at the bottom and the hot air would not be at the top, because there is no bottom and there is no top inside that jar. There is just air, pulled by gravity, and the denser stuff settles. That is not the air making a choice. That is gravity making a choice for it. So a candle flame, sitting in your kitchen, is being shaped by gravity. The little teardrop of fire, that little pointed shape, exists because gravity is reaching into the room and grabbing the cold, dense air and pulling it down past the hot reaction zone. The cold air slides down along the sides of the flame, gets under the flame, and pushes a column of hot reaction product upward. That column carries away the hot soot, stretches the flame out into a long, thin, pointed shape, and dumps the heat and the carbon dioxide up toward the ceiling. Without that column of falling cold air, the candle could not even breathe. Let me say that again. The candle cannot breathe without gravity. The way a candle gets its oxygen normally is that the column of hot rising air leaves a kind of low-pressure pocket, and fresh cold air, full of oxygen, falls in from the sides to fill it. The candle is being fed by buoyancy. The flame is sucking new oxygen in by virtue of sending old combustion products up. The whole shape of the flame is a chimney, a miniature self-sustaining chimney made of the air itself. Take that chimney away, and the candle starts to suffocate. This is going to come back. Hold it. Now, before we leave Earth and go to space, I want to stop for a minute and tell you about one of the greatest demonstrations in the history of teaching. There was a man named Michael Faraday, an Englishman, born poor, mostly self-taught, the son of a blacksmith, who became one of the greatest scientists who ever lived. And every Christmas, in London, Faraday would give a series of lectures for children. Just children. He would stand up at the lecture hall and demonstrate experiments and explain physics. And one year, in 1860, Faraday gave a series of 6 Christmas lectures titled The Chemical History of a Candle. 6 lectures about a candle. Just a candle. A little stick of wax with a string in it. He pulled more out of that candle than most professors pull out of an entire textbook. He showed how the wax was a hydrocarbon. He showed how the wick capillaries worked. He showed what the dark zone was, what the bright zone was, where the soot came from. He proved that the flame produced water by holding a cold spoon over it and showing the condensation. He proved it produced carbon dioxide by collecting it and tipping it out into lime water. He weighed the candle. He timed it. He cut it open. He brought the candle indoors, took it outdoors, lit 2 of them at once, watched their flames join. And out of all that, 6 lectures worth, he laid out almost the entire architecture of basic chemistry. From a candle, Faraday said the candle was the perfect entry into science because it had a little bit of everything in it. A little physics, a little chemistry, a little fluid mechanics, a little optics, a whole universe sitting on a table in the dark. He said something to the effect of, "You cannot study a candle and not become a philosopher." I want you to hold that idea. Faraday looked at a candle and saw the entire physical world in it. He did not yet know about microgravity. Nobody had been to space, but he had already figured out that the shape of the flame, the up-pointing teardrop, was due to a current of air rising through it. He even drew it. He drew a candle with arrows showing cold air flowing in from below and hot air streaming out the top. He understood, in 1860, that a candle is a chimney. He just had no way to test what would happen if you turned the chimney off. We can test it. We have tested it. And the answer is wild. Let us turn the chimney off. Let us go to space. Imagine you are floating inside a spacecraft. Everything around you is in free fall. The whole vehicle is falling around the planet. And you and the air and the walls and the candle are all falling at exactly the same rate. So inside the cabin, things just float. There is no down. If you let go of a pen, it stays where you let it go. If you blow a puff of breath, it does not fall, it does not rise, it just hangs there as a little rotating cloud of warm air, very slowly mixing with the rest of the cabin. Now strike a match. You can. It works. The chemistry of the match head, the friction, the little flare of phosphorus, all that works fine. None of that depends on gravity. The match lights, and you get a little burst of orange flame. But the flame in your hand looks wrong. It does not climb. It does not lengthen. It does not point. The first thing it does is shrink. The bright part contracts down toward the match head, and what is left is a little rounded pillow of pale yellow blue, sitting around the match like a ghost. There is no teardrop. There is no plume. There is no smoke trail. Just a smudge of light that fattens into a ball. Hold the match still, and the ball gets rounder. It is not a sharp ball. It has a slight bluish edge and a dimmer yellow interior. It is dimmer than any candle you have ever seen. It is so dim in some experiments that the cameras barely pick it up. It is only a few centimeters across, and it does not move. Then, after a few seconds, it goes out. It just smothers itself. Why? Because the chimney is gone. The candle, on Earth, breathes by buoyancy. The hot air goes up, the cold air falls in, and that flow constantly delivers fresh oxygen to the reaction zone and sweeps away the carbon dioxide and water vapor. Take away gravity, and the hot air does not go up, because there is no up. The combustion products just sit there. They form a little envelope around the flame, choking it. The fresh oxygen cannot get in. The exhaust cannot get out. The flame is sitting in its own breath. The only way oxygen reaches the flame, in microgravity, is by diffusion. Diffusion is the slow, random wandering of molecules from regions where there are a lot of them to regions where there are not so many. It is what makes a drop of food coloring in a still glass of water spread out over the course of hours. It is what carries the smell of bread across a kitchen even when there is no breeze. It is real, it works, but it is slow. Compared to a buoyant chimney sucking in liters of fresh air every second, diffusion is molasses. So the flame in space gets only as much oxygen as can wander into it through random thermal motion. That is enough to keep some kinds of combustion going, but the reaction is starving. It is on a diet. It is gasping. So it burns cooler and dimmer and smaller and rounder. Why round? Why does it form a sphere? Because diffusion does not have a preferred direction. If oxygen has to wander in by random walk, it wanders in equally from all sides. North, south, east, west, up, down. Meaningless terms here, but you get the idea. The flame eats oxygen evenly from every direction. So the reaction zone forms a thin shell at exactly the radius where the diffusing oxygen meets the diffusing fuel vapor. And because diffusion is symmetric, that shell is a sphere. A perfect, glowing, spherical shell of chemistry. That is what fire really wants to be. That is fire's natural shape. We just never see it on Earth. Because gravity is always there, always squeezing the sphere into a teardrop, always making fire look stretched out. The pointy candle flame is not the real thing. It is fire being yanked on by gravity. Take the gravity away, and the yanking stops, and the flame relaxes into the shape it was always trying to be. I find that almost shocking. Every fire I have ever seen in my life has been deformed by gravity. Every match, every campfire, every candle on every birthday cake, every burning leaf. They are all the same chemical process, all forming little distorted versions of the spherical truth. We have spent our entire lives looking at the warped shape and assuming it was the real shape. Now I want to slow down here, because I think the implications go further than people realize. Once you accept that gravity is shaping the flame, you start to see other things gravity is doing. For instance, the color. A candle flame on Earth is bright yellow-orange. The reason it is yellow is, again, soot. The flame on Earth is full of these tiny soot particles that get heated up and glow. They glow because they are hot, just like a piece of iron in a forge glows red, or yellow or white depending on temperature. Glowing because of temperature, that is called incandescence. The yellow of a candle flame is incandescent soot. Where does the soot come from? It comes from incomplete combustion, carbon atoms that did not find an oxygen partner in time. They stay together, clump into tiny grains, fly up through the flame, and glow. If they do not finish burning, they leave the flame as smoke. That is what smoke is, mostly. Soot that did not combust. In space, the flame burns slower. The chemistry has more time to find its partners. There is less leftover carbon. Less soot forms. So you get less yellow. The flame is more blue. Sometimes the flame is so dim and so blue that astronauts have reported it being almost invisible. They could only tell it was there because their thermometer said so, or because they could feel the heat with their hand near it. Imagine that. An invisible fire. A real fire. Burning. Generating heat. Consuming oxygen. Producing carbon dioxide. And you cannot see it. That is not just a curiosity. That is a serious concern in spacecraft design. If a fire breaks out aboard a vehicle, on a ship, on a station, you want to be able to find it. On Earth, fire announces itself with light and smoke and a rising plume. In 0G, fire might be a small, invisible, glowing ball, not climbing, not producing visible smoke. The first you know about it might be when something nearby gets hot enough to fail. People who design spacecraft fire detection systems have to think about all this. And there is more. There are kinds of flames that are very, very hard to study on Earth, because gravity messes them up. So scientists have done combustion experiments in space specifically to see things they cannot see down here. One of the strangest things they have found is what is called a cool flame. Now that is a strange phrase. Cool flame. A cool flame sounds like a contradiction, but it turns out that some hydrocarbons, under the right conditions, will undergo a kind of low-temperature combustion. They will react with oxygen, slowly, producing a faint chemical glow, generating modest amounts of heat. The reaction is real combustion, but it is not the kind of full-throttle, high-temperature, soot and light show you usually associate with fire. It is gentle. It is dim. It can sometimes be too cool to even feel hot. And on Earth, these cool flames are unstable. The buoyant currents stir up the gas, the temperature shifts around, and the cool flame either gets hotter and turns into a normal flame, or it goes out. But in space, with no buoyant currents, the conditions are stable. And astronauts running combustion experiments have observed cool flames lasting for minutes. Pale, almost ghostly things. They have observed droplets of fuel that looked like they had stopped burning, that all the visible flame had gone out, and yet the droplets continued to shrink. The droplets were still being consumed. There was still combustion happening, but it was so cool and so dim that it was below the threshold of vision. A fire so calm you cannot see it, but it is still eating its own fuel. Think about how strange that is. We have a thing on this planet called fire, which we have been familiar with for millions of years, since before we were even our current species, and it turns out that the fire we know is only one kind. It is the gravitationally stretched, soot-laden, brightly glowing version, and in microgravity, fire reveals other versions of itself. Quieter ones, cooler ones, spherical ones, invisible ones. There is a whole zoology of fire we never knew about, because we never got to see it without our own planet's pull warping it. I think this is the part of the story that gets me most excited. We did not have a choice about gravity. Gravity is the scenery on which all of human science was developed. Every experiment ever done by anybody before about 1960 was done in a 1G environment, with weight, with buoyancy, with rising hot plumes and falling cold ones. So all our intuitions about how heat and chemistry and fluids behave got built in that environment. And when we finally, briefly, in only the last few decades, got the chance to do experiments without that constraint, we discovered that some of the things we had taken to be deep facts about fire and heat and air were just facts about Earth. Heat rises. That is not a fact about heat. That is a fact about heat in a gravitational field with a denser fluid around it. Take that situation away, and heat just sits, or wanders, or diffuses outward in every direction equally. Smoke goes up. No, it does not. Smoke does not know which way is up. The hot air containing the smoke is being pushed by gravity and buoyancy in our world. Take that away, and the smoke just expands in a slow spherical fog. Fire is yellow. Sometimes, when it has soot in it. In space, often, fire is blue, or pale, or invisible. A flame points. It does not. Pointing is something gravity does to the flame. Pointing is the flame's response to being yanked. I want to go further. Let me push this idea harder. Why do you suppose evolution gave us the intuition that hot things rise? It is because we live on a planet with gravity, and our ancestors needed to know that smoke from a fire would warn them, that heat from below would keep them alive, that hot air would rise out of the cave through the chimney slot. That little kernel of physical truth got baked into how we think the world works. It feels obvious. It feels like a property of heat itself. But it is not. It is a property of heat in a particular environment. And the moment you change the environment, the rule breaks. How many other intuitions of yours, I wonder, are like that? How many things that feel like deep truths about the universe are really just facts about your particular corner of it? I do not know the answer, but I suspect it is a lot. And every time we get a new vantage point, somebody finds another rule we thought was a law and discovers it is just a habit. All right, let me bring this all back to the candle, because I do not want to leave you in the abstract. Let us picture the thing one more time. Imagine a candle on your kitchen table. The wick is lit. The flame is doing its little dance, pointed up. Yellow, warm, comforting. You watch it. You think you understand it. But now, let us pretend you have a knob in your hand. The knob says gravity on it, and it goes from 1 to 0, and you start, very slowly, to turn it down. At gravity equals 1, the flame looks normal. Teardrop, bright, flickering a little. Turn it down to gravity equals 1/2. The flame gets a little fatter. The teardrop gets shorter and rounder. Because the buoyant convection is weaker, the column of rising air is slower, and the flame does not get stretched as far. Down to 1/4. Now the flame is a chubby flame, almost mushroom-shaped. The yellow is duller. Soot has more time to burn off, so less of it survives to glow. The flame is dimmer. Down to 1/10. The flame is now nearly a sphere. There is a little bit of asymmetry, a little hint of a tail, because there is still enough buoyancy to bias the flow. But mostly it is round. It is mostly blue. The yellow is almost gone. The flickering has stopped, because flickering is itself caused by instabilities in the buoyant column, and the column is now very weak. Down to 0. The flame is a perfectly round ball, pale blue, glowing faintly, steady as a pearl, not moving, not pointing, not flickering, sitting there in midair like a soap bubble of fire. A little blue moon, orbiting nothing, and it is dying. Slowly, because it cannot breathe. Within a minute or two, depending on the size of the chamber and the freshness of the oxygen and the airflow inside the spacecraft, the flame will fade. The blue will get paler. The sphere will shrink. Eventually it will wink out, leaving a little wisp of unburnt fuel and a region of carbon dioxide where the candle used to live. That is fire on its own terms. That is what fire does when you stop tugging on it. Now turn the knob back up. As gravity returns, the sphere wakes up. The cold air starts falling. The hot air starts rising. The sphere stretches. The teardrop reforms. The yellow soot blooms. The flickering returns. The flame brightens. It points. It points up. But you and I now know what that pointing is. It is not the flame trying to reach for the sky. It is gravity reaching down through the air and rearranging the burning gas. The flame is not lifting itself. The flame is being pulled by the cold air falling around it. The pointing of a flame is, secretly, a downward motion made visible by what gets shoved out of the way. Every flame you have ever seen has been pointing up because something was falling down past it. The candle is a kind of magic trick that gravity does on heat. Let me leave you with one more thing, and then I will stop. You know what I find lovely about all of this? It is that the answer to a question as simple and stupid as why does a flame point up turns out to involve gravity, buoyancy, density, diffusion, fluid mechanics, combustion chemistry, and the geometry of free space. To really answer it, you have to understand a half-dozen different fields of physics. And you have to be willing to take the question seriously, instead of waving your hand and saying heat rises and walking away. Because heat rises is not an answer. Heat rises is the question dressed up to look like an answer. The actual answer is that gravity makes cold air heavier than hot air and pushes it under the hot stuff and shoves the hot stuff up. Faraday knew this. He could not test it in 0G, but he could draw the arrows. He could see the chimney. He understood that the candle was an architecture of currents, not a column of fire. What I love about him, and about the kind of thinking he was doing, is that he refused to be bored by the candle. Most people, given a candle, do not look at it for very long. They light it, they have dinner, they blow it out. Faraday looked at it for 6 lectures worth. He looked at it long enough for it to stop being ordinary, and what he saw, and what we have only confirmed in the last several decades by lifting candles off this planet, is that the ordinary things have the universe inside them, hiding in plain sight. The next time you see a candle flame, I want you to do something for me. I want you to tip the candle a little. Watch the flame curl back to vertical. And as it does, picture the cold air pouring down past it from above, draining around the sides, gushing in underneath, and lifting the column of hot reacted gas straight up like a chimney lifting smoke. The flame is not climbing. The flame is being pushed up by an invisible river of falling air. And then imagine, just for a moment, what it would look like if you could turn that river off. The teardrop pinched in, the point dissolved, the whole thing collapsing inward into a small, blue, perfect sphere of fire, sitting calmly in the middle of nothing, breathing as gently as it could on the little oxygen molecules wandering by. That is what fire is when you let it alone. Quiet, round, almost shy. We just never get to see it, because we live on a planet that will not stop pulling. So tell me what you think. If you could take a candle anywhere in the universe to study it, where would you take it, and what would you want to find out? I would love to hear your answer.